Let's start class. So last time we talked about brief introduction for the R, and I think we stopped here. Yeah, we moved to the graphics, plotting in the R. So for the histogram, this is a very commonly used type of plots that break the data into different beams and then displaying the distribution of the numeric data. Okay. So this is histogram is for the numeric data. Bar chart, on the other hand, is for the categorical data. So the number of breaks and the classes we can define. So the user can choose how many breaks or how many classes, how many beams for this histogram. Sometimes it really matters. So if you set different number of beams in the histograms, the shape may be some difference. Okay, so that's why using the histogram sometimes is tricky. You need to try a few different numbers. So this is the still the that car data set. So we're examining the MPG on the highways. Here I just have 3 beams, and here about 10 to 20. So I set the N class is 20. But if I set this is 20, that doesn't mean it's exactly 20. It's close to that. So it looks slightly different, right? Because in the threes, you only see the monotonically decreasing for the height of the beam. But for the 20s, then you can see it start with low and increase, then decrease. So you have more information. So this is the histogram, but histogram is to show the distribution of the of a data through the discrete number of beams. Okay, so another way is to smooth out the height of the beams. So to make it a smooth curve, that's called densities. So we can compute the smooth densities based on the observed data. Okay, and here this is the density curve for the car data set. Okay, so unlike these are discrete, so you can see the height are not continuous, has a jump or drop, but here is smooth. Okay, so the densities curve can be plotted in R very easily. You can use the density function. So that calculates the smooth densities of based on observed data points. However, the density is not just depend on the data, it also depends on how much smoothing you need to have. You want to have the density curve very smooth or a little bit smooth. So the smoothness is what we call in statistics as a tuning parameter. Okay, so it can tune how much smoothness we want to have. So look at here for this one, the one on the lower right, that's the smoothest. Okay, so it's very smooth. Although the data itself is discrete, we have only 93 data points, but the plotted smooth density curve is very smooth. It's very close to the normal, but we can be less smooth. Like this one is the least smooth. That spikes corresponds to the observed data points, maybe multiple points around the same locations here. So how do we choose? Yes, right? So that's a very important questions. So we will talk about that later in the course. But here, what you can do is, before we reach that point, so you can try different smoothed density curves. Okay, and how do we choose the smoothness? So that depends on the functions. So here, if you use the density functions in R, so there is a tuning parameter called a BW, that's the bandwidth. And there are some other functions in R and in our package can also do the density smoothings. So they have different functions. So different functions, they have different parameters. So here, if you use the density function, that function is in the base package. You don't need to install any other libraries, just the base package. You install R and you can do that. So the bandwidth is related to the smoothness. So if the bandwidth is small, that means it's less smooth. If the bandwidth is large, it's more it's smoother. Okay, so it adds smoothness. So here by default they will use the Gaussian kernel. Okay, so what does the smoothness? How does the underlying algorithm calculate and find out the smooth densities? So that is based on there's a term called moving average. Okay, so but this average is weighted. Okay, so let me see. Let's see. Suppose we have some data points here, right? And obviously around this range, we have more data points. So most of the data points occurs here, right? So what it does is it used a Gaussian kernel. Gaussian kernel is like a bell-shaped curve to put on the weight. Okay, so if we want to estimate the density at, let's say over here, at 25, let's say when the x is 25, we will put on different weights for this x using the Gaussian kernel as the weighting function. So obviously, if we have more data points around this point, around 25, then the density, of course, will be higher. But if we have less points around 25, the density will be lower. And why it's smooth? Because the weighting function is smooth. So that's why if you move to the 26, the weighting function also moved to around 26. So the peak is at 26. So you can see it's just moving these weighting functions and then weight it and then find out the densities. So that's why if you look at the whole spectrum, so it will be a smooth density curves. But the bandwidth is related to the spikiness. So if the bandwidth is small, so the Gaussian kernel function, so the weighting function will be very spiky, like this one, or maybe even more spiky, like this one. So it will have more weights just around these points around the peak, but it drops sharply. But if we have a large bandwidth, it will be much flat, much smooth. So in that way, the computed density function will be much smoother. Okay, so that's why you can see when the bandwidth is 25, when the bandwidth is 1, and when the bandwidth is 5, you can see the smoothness changes. If we have large bandwidth, it's very smooth. Small bandwidth, it's less smooth. But this one, I use the default. So the algorithm itself has its own default values. But you can easily see the default value is what? Is a little bit bigger than 1. It's but close to 1, but less than 5. Right? So which one we should choose? I would say before we talk about like cross validations later, so what we can do is you just try a few different levels for the bandwidth and then see which plot makes the most sense. Then just use that. So that's the density. And the scatter plot. Scatter plot is the most common way to display the bivariate numeric data point. So you can see here we have the x-axis have the MPG, and the y-axis, the vertical axis, has the price values, right? And also, actually, we can have the third variable incorporated. Okay, so if the third variable is categorical, like here, if the third variable is highway or city, so the MPG is on the highway or in the locals, then we can just use different point characters and different colors. Like here, you can see the blue ones is the MPG at local, and the red open circles are the MPG on the highways. So that is a way to have this additional variable, which is categorical variable here. Okay, so here we need to have the type of the plots. So that will be the so it has different types of scatter plot. If you see when the type is n here, I'm just opening a blank scatter plot, then make the points, then add on the points. So you can see then I add on the points. So plot is a high level graphic functions that creates a plot. But the points is the low level graphic function that adds the points to the existing plot. So that's why I said the type is none. So just create the x and y axis with the label with the axis labels, but not doing the plot. So then I can do the add the points using the points function. And then I can also put the legend on the top right. So that's the legend. So you can see these points, legend, these are the low level functions. And this is the high level graphic function. And of course, the type has other types like the P. P, if the type is P, it will have the points. And if the type is L, it will be the lines, connect the points. Okay. And also it has a H that will be like a histogram type of the scatter plot. And you can explore these different types. Okay.
I have a question, Dr. Lee.
Yeah.
When inputting this information into, we have to follow this order, right? From highest level to lowest for it to compute properly, correct?
Oh, you mean this data we have to put them in the order?
Yeah, like
No,
from
no.
plot to points to points to legend. I can't just start with my points and then try to plot it. I need to go in order, right?
Oh, yeah. That's right. First, you have to have a high level graphic function to create a plot. Then you add these low level graphic function to add to the existing. You cannot start with the low level. That's right.
Right, thank you.
You're welcome. Okay. This one is adding the text to the existing plot. So just like the previous one, we have the plot to create a new plot, then add points, then add the legend, and then after that, we label the highway data, okay, using the text function. So you can see the points, legend, text, these are all the low-level graphic functions, which adding either the points, legend, or the text. Okay, so you can play with this data after class. Okay, so this is the bubble plot, we call it. So this is, so the bubble plot is a nice way to have this like the scatter plot, but adding the third numeric variables information into the plot. Okay, so we have the mile per gallons, we have the price, but if we also want to include the engine size into this plot. So what we can do is we can use the bubble plot. So that is called a symbol. So this function can have the scatter plot, but the circle equals to the engine size. So this is the x variable, this is the y variable, and the circle equals to engine size. That means the size of the circle is proportional to the engine size. So basically we have three variables information in this plot. Okay, so that is a good way to have one plot that includes three numeric variables information. And this is the adding the lines. So here we have the 100 over MPG and against the weight. And then I fitted two curves. One is the least square line. So that's the linear regression line. That's the blue one. So you can see the blue one is a straight line. That's the linear regression line, fitted based on this data set. And also I used a nonlinear smoother called the Lowy smoother. We will talk about the details in maybe next week. Okay, so the Lowy smoother is a smoother that can output the smooth but nonlinear curve. Okay, so you can see the red curve, that's the Lowy smoother. But even though it allows nonlinear curve, you can see the Lowy smoother fitted curve is very close to the straight line. So that implies what? That implies the relationship between the weight and the inverse of the MPGs. Almost linear, right? So that shows a good example. So here, that shows a good example that the difference between the lines and app lines. For the app lines, that only can allow us to plot to add a straight line, not a curve. But the lines allows to add a curve. Okay, and both of them are the low-level graphic functions that adds the line or curve to the existing plot. Okay, so if we have more than two variables, let's say we have four variables, or maybe even more, how can we display all these variables? And particularly if we are looking at the pairwise relationships among these numeric variables. Okay, so here, this is a very good way to display the multiple numeric variables and their pairwise relationships. That's called a scatter plot matrix. Okay, so here we have four variables. We have the MPG locally and the MPG on the highway and the horsepower of the cars and the price of the cars. Okay, so how to read these plots like here, this one? What is the axis? What is the x-axis? What is the y-axis? It's not difficult to find. For the x-axis, the horizontal one, you can see it should be the MPG city. For the vertical one, you just move to here. That's the MPG highway. See that? So this is the MPG highway. This is the MPG city. And they have a very strong linear relationship. And that is obvious, right? Because that's the same car. And for this one, you can see the vertical axis is the horsepower. And the horizontal axis is the MPG dot city. And you can see there is an inverse relationship. Okay? So that is a good way to display the multiple numerical variables. Okay, and this function is in the base package called the pairs. So you can see this is the sample code, and to do the scatter plot matrix. And this is a fancy version of scatter plot matrix to compare. Here, this one, we just have one data set, but this one can also compare different groups. Okay, so here I used a function called the scatter plot matrix function, not in the base package, but in the R library, or in the car library. Okay, so you need to install the car library and then open that. And then you can use the scatter plot matrix function to do this. So here, there is a, if you have group, so if then you can put the group variable after the column. So the cylinder here is showing the grouping variable is based on the number of cylinders of the cars. But here we have four variables: the mpg.city, mpg.highway, horsepower, and price. Okay, so this is the group variable, and you can also define the colors for the different groups. I use the red and blue. So you can see here the red one is 4-cylinder cars, blue one is the 6-cylinder cars. Okay, so the one that on the diagonals is showing the density plot. Remember the density plot for the two groups of, of that variable. Like here, this shows the mpg.cities density plot. So you can see the mpg for the 6-cylinder cars is lower, is smaller than the 4-cylinder. But that is obvious, right? So this is a fancy version of scatter plot to compare the groups. And also, if we don't want to compare, do the pairwise scatter plots among all the variables, we just want to show this data set, which has multiple numeric variables. So what we can do is we can use the parallel coordinate charts. That is another type of plots that is suitable for the high dimensional data. So still I'm using the car data set, and the function that I do the parallel coordinate. Of course, there are other functions in the R and the packages in R can do the similar job. Okay, so I'm using the par coord that is in the library mass. This one is in the library mass, and I used this library before. Remember, for the Quine data set, that's in the library mass. Okay, so this function is in this library. So you can see the plot is like that. Okay, so here the color, here I set the color is the, let's see, is the, I think the color is based on the cylinder size also. Yeah. So anyway, so you can see the plot that shows the price, MPG, cities, highways, engine size, and the fuel tank capacities on two groups. The group is based on the number of cylinder size, and you you can see the here you can compare these two groups for the different colors, and you can see the red one probably is most likely the cylinder size is 6, and the green one is the 4-cylinder cars, so the MPG is higher, and the MPG, but engine size for the green ones is lower, right? And the fuel tank capacity is also the green one tends to be lower. Okay? And the price, the housing price, they have some overlaps, but in general, for those cars with low MPGs, tends to have higher price, right? So you can interpret easily through this parallel coordinate chart. Okay, and so these are for the high dimensional data, and next is to display the large sample size data set. Okay, so if we have a large sample size, let's say we have 10,000 data points, even it's just from a very simple distribution like X is from normal, standard normal distribution, Y is from standard normal distribution. But just because we have 10,000 data points, and if you do the scatter plot, you really cannot see much in this black area because it's too dense. You cannot see much, right? So what we can do is for these large sample size data set, we can use there's a function called a hex bin in the hex bin libraries. So first, I need to install these libraries, and in that library there is a function called hex bin. Then it will binning the X and data points. Okay, so the each beam can contain at most 50 data points. Okay, and the darkness is proportional to the number of points that falls into that beam. Okay, and then I can do the plot for these beams. And you can easily see that the center of these distributions, Biver distribution, is around 0 and 0. X is 0, Y is 0. And that's obvious because X is from standard normal, which has the mean is 0. Y is also from standard normal, which mean is 0. So this looks much better than looking at this, right? So that's one way to display the large sample size data. And also we can display the large sample size data using transparent data point. Okay, so when we do the scatter plot, the color, COL, that's the option for defining the color. That actually can be defined through 4 numbers in the RGB function. RGB function in the R defines the colors. So the first input value, the first argument is the redness. So that is between 0 and 1. So 1 is in pure red, 0 is no red. So that means like a white. Okay, so this defines the second one defines the greenness, green. And the third one is the blue. And the last one to the fourth one, so the fourth one is the alpha value. That defines the transparent or not. Okay, if the alpha is 0, then it's fully transparent. If it's 1, then it's open. Okay, so here I choose the alpha to be 0.1. So if it's fully transparent, you cannot see that point. So I set it to be 0.1, and then I do the scatter plot. So even though we have 10,000 data points, so you can still see quite better than this one. Okay, so you can see the center is around 0 and 0. Right? So that is another way to show the large sample size data set. Okay, any questions so far? Yeah, how large? That's a good question. So really, it depends. If it's like a few thousand points, so first what you can do is just do something like that. If that doesn't look good, that means the sample size is kind of large. So what you can do is you can think about either using this approach or this approach. So which one is better in terms of for this hex bin approach? This actually can handle even larger sample size, like not just 10,000. If you have 1 million, you can still handle that because the beam size can increase, not just 50, can increase to 500 or 5,000. Okay, so this approach can be used for even larger sample size. But for this one, still it's better than this, but still limited by the sample size. Okay? And also, if you saved as a PDF file or saved as a JPEG, this figure file, then you will see that if we have large sample size, the file size can be very large. But if you use this approach, the file size will be much smaller because this is not displaying each data point, but displaying the beams, that hexagon beams. So this is this will have a much smaller file size if you save that uh, uh, save this plot as a file. Okay, for the sometimes when we create a plot, we want to do something like the Photoshop does. So we want to overlay the figures, right? So like here, we have a contour plot. That's the X and the Y's. These are the spatial parameters that defines the locations, and the contour shows the height of that location of each point. Okay, and this is a mountain. Okay, so here what I did is first I used the image file to do the uh, plot just using different colors. Okay, so use the image function to have the two-dimensional plot, but the higher place will have the yellow and the lower place will have the red. And then I can add the contour lines onto the existing plot. So what I do is I have first do the image, so that only plots the uh, yellow-red plot that use the color to show the height of the locations. And then I can add the contour lines by using the contour functions with the X and Y's are the horizontal and vertical axis, and the height is represented in the Z. And but I have to add add equals to true. So that means this. So this function can be a low level and it can also be a high level graphic function. It can create a contour plot. It can also add to the existing plot. So what it does is if you have the add equals to true, then this one becomes a low level graphic function. It will just add an additional layer to the existing plot. Okay, so then you can see the contour lines. And we can also overlay the figures using the new equals to true. So here is an example. So suppose you want to have a figure that which includes two plots, but these two plots are in different size. You can see the top one is much larger size compared to the bottom ones. So if you don't specify the size by default, each plot will have the equal size, right? But here I want to have an unequal split. Okay, so what I can do is first I set the frame, and then I use the fig option in the PAR function. So fig is to define the NDC coordinates. So what does that mean? That means first, let's say the fig equals to 0, 1, 0.4, and 1. So that first defines the location for this one. Okay, so what it does is, so the entire plotting space, let's say, is here, right? Okay, so first the 0, 1 is defining the x-axis. The x-axis at this point and this point. So these 2 points. So this one start with 0. So that means this one starting with the left end. Okay, and the 1, that means this goes to the extend to the right end. So the 0 means starting at the lower left corner, and the 1 goes to the right corner. Okay, and then 0.41, that shows the y-axis, y values. Okay, so for this point, the y is at the 0.4. Remember, the entire height is from 0 to 1. Okay, so this one start at the 40% of the height for the total plotting area. Okay, and this, then the last one is the height for this point. So that goes to the top. So that's the NDC coordinates. So it specifies the x and y locations for these 2 points. If we define these 2 points, this plot is located, right? So then you can see, since we set the y at 0.4, so this one will have contains 60% of the height for the total space, right? Plotting space. Okay, and then the next one, after that, I set the par with new equals to true. So that means we will add the second plot. Then the NDC coordinates is 0, 1. So that's the coordinate for this plot. Still 0 and 1. That's the x-axis for this and this, for the x-axis. So it starts with left end, it goes extended to the right end. So 0, 1. Okay, then followed by 0, 0.4. So this this point start at the bottom, goes to up to the 0.4. Okay, so this is the how we can have the unequal split of the plots. Okay. Any questions so far? Okay. This is an illustration of the central limit theorem, and this is a good example for doing the plots, and also central limit theorem is probably the most important theorem in the statistics, I would say. So what is central limit theorem? Of course, this course is not about teaching these statistical theories, but just as a good opportunity. So central limit theorem says what? Says that if the data points are collected from a population, right? Let's say we are collecting the fish from the university lake, okay? And we are measuring the length of each fish, okay? Let's say, suppose in the population, all the fish in the university lake, So that will be what? I would say it's probably will be skewed to the what? Skewed to the right. Is that right? So probably will, so if we plot the length of the fish in the university lake, that will be something like that. Why skew to the right? Because there must be some very large fish in the lake, but most of them are quite small. So that's why it will be the skew to the right. Okay, so the population itself is not normal. It's not bell-shaped. What is normal? Normal is bell-shaped curve. It's symmetric around the mean. Of course, it's not. Okay, it's skewed to the right. So even though the population distribution is not normal, it could be skewed, it could have some extreme outliers, it could even be discrete. You will see in the homework one, I also want you to to implement this for the discrete distribution, like a binomial distribution. We know binomial distribution is not continuous, it's discrete. Okay? Even though the population is not continuous. Okay? Okay, now that's the very general settings about the population distribution. But then the central limit theorem is very powerful. It says that you don't care about the population distribution is normal or not. As long as you give me some sample from this population. Okay? And if the sample size for this data you collected from that population is large enough, and you may say, how large is large? By the general rules, we usually consider 30 observations as adequate sample size. Okay, let's say if the sample size is 30 or larger, then no matter what the population distribution is, discrete, not discrete, skewed, it doesn't matter. The sampling distribution for the mean will follow approximately normal. So what does that mean? That means, so here we have these 30 data points, let's say, and we have a mean, we have an average, right? We can have a, like we caught 30 fish from the lake, we measure their length, we have a sample mean. Let's say the average length for the base from 30 fish that I caught in the lake is about, let's say, 2.5 inch. Okay. But if you caught another 30 fish, that average will be what? Will be different. Is that right? It may not be 2.5. It may be 2.7 or 1.9, something like that. So you can say this X bar, this sample mean is a random variable. Is that right? Because we can catch repeatedly from the population if we can. Then this sample mean will be different because it depends on the random sample. The sample is random, so the mean also random. So this X bar sample mean is random. So if a random variable, it follows a distribution. Does that make sense? If we have a random variable, it always follows a distribution, right? So that distribution for the sample mean is called the sampling distribution of the mean, which magically, no matter the population distribution is, that sampling distribution, that sample mean has the distribution which will be approximately normal. So that's the power of the central limit theorem. Okay, so here I'm showing you one example which is generated from a skew to the right distribution. That distribution has a name called the gamma distribution. Okay, so I generated the X from the gamma distribution. So the left panel shows you the histogram and also the fitted density curve based on 10,000 realization random sample from the gamma distribution. So you can see it's skewed to the right. Definitely not normal. definitely not symmetric. But then, based on these 10,000 data points, okay, so I randomly get, each time I randomly sampled how many I randomly here I randomly sampled 50 data points from these 10,000 data points. 50 from this, 50 from this. Each time I get the mean for each 50. Okay, then I plot the histograms. That's the histogram for the sample mean. And you know, histogram is an approximation of the smooth density curve, right? So the blue curve is the fitted density curve based on the observed sample mean. So you can see now the mean, the sample mean follows a bell-shaped curve, and that's the central limit. That's one example. So that's is a computer experiment that's showing you how the central limit theorem works. Okay, and so go back to the homework. So in the homework, I ask you to repeat this, and this is for different sample size. For the previous one, I set the sample size is 50. Now here I'm setting the sample size is 3. So each time I'm just sampling 3 data points and get the mean. So now you can see the sampling distribution for the mean is not normal because that's too small. But if we have 10, it's better than this, but still worse than 50. So that's why usually in practice we say 30 is like a threshold. So that shows the sample size effect on the approximation to the normal. So in the homework 1, the third part is to apply the same idea of here. Then this time the population distribution have 3 types. One is the normal, one is the exponential, and one is the binomial. This one is discrete. And these two, the first one is normal, is symmetric. Okay, and the second one is skewed to the right. Okay, so apply the same idea to these 3 distributions. This as your third part of your homework 1. Okay, so I have some detail. If you have any questions, you can let me know, send me an email, and I will try to answer that. Any questions? And homework 1 is due next Friday. Okay, so that's the first homework. So I'm having a little longer than 1 week. So you can have enough time to work on that. And from the second homework, I will have just 1 week span. Okay, if you don't have any question, let's continue. So this is the apply function, which is very useful. And this is actually a family. So it has a few apply function called L apply, S apply, apply, and T apply. That applies, these functions can be used in different situations. So apply family is used to efficiency relative to the explicit loops. So it's very efficient for the programmings, if you know this, and convenient that simplifies the code. Like here, this is a very well-known data set called iris data, and it has these 5 variables, it, including 3 species of iris. Okay, so it has Setosa, Virginica, and another one. So the first 4 are the numeric measurements, the sepal size and the sepal width and the petal size, petal width. So here I want to find out the mean of these 4 numeric variables. What should we do? We can calculate one by one, but a simple way is just using the apply function, and apply function for the iris data, but subtract the 5. Why? Because the fifth column is what? The fifth column is not numeric, it's categorical. That mentions the species of each sample. Okay, so of course you cannot find out the mean for this one. So that's why I eliminate the fifth column, and then the second argument only allows two values, 1 and the 2. 1 means by row, 2 means by column. Okay, so that means the operation is by row or by column. And the third one is the function that we want to apply. So here I want to get the mean. So that tells R that we want to find out the mean for each column for these 4 columns. Okay, but if I change the 2 to be 1, if I change this to be 1, then I will find out the mean for each row. That will be different. Okay, so that's by row and by columns difference. So you can see using the apply, it can quickly gives you the 4 variables mean. Okay? And we can also apply in different situations using the t-apply function. So t-apply function is used for the rect arrays to represent a combination of a vector and the labeling factors. For example, in the Quine dataset, we have these 5 variables. Suppose we want to know the average number of days of absence for each age group. Remember, we have 4 age groups, right? For the age groups, we have 4 age groups, F0, F1, 2, 3. Okay, and this is the number of days absent for each student. So here, if we want to get the average number of days of absent for each age group, then you can use the t-apply. T-apply days, that means we want to get the average number of days, but followed by the age. Age is the grouping variable. We have to get the average number of days for each age group. And the function is the average. We want to get the average number of days. So that's, we'll calculate the average number of days. Okay, and we can have more complicated, not just for the age group, but the age and gender group. So now we have very similar to this, but instead of using the age, we use the list, parentheses, sex and age. Then it will have the average number of absence for each age and gender combinations. So you can see using the t-apply can be a very convenient way to find out summary statistics. Okay, that especially related to we have a grouping variable or more than one grouping variable. And that's not just for the mean. You can change it to the median, change to the standard deviation, change to the variance, all works. Okay, so it's so that's why I think this is a very useful function family that you probably should know. And this one is the L apply and S apply that operates on the components of a list of vectors. And this one you can take a look, which is not difficult to understand. So I will just move to the next. Oh, yeah, I think this one is quite obvious. It just S apply is more user friendly. So if I use it, I will usually use the S apply, but L apply always return as a list. Okay, importing the data sets. So R has many ways to import various types of data. Okay, so like the most common ones is from the Excel, right? Or the TXT files. So these are the basic and very commonly used data format. So if it's a TXT file, then you can just use the read.table. So that's the function which can reading the TXT files or the DAT files, so these text files. But here, you have to be very careful. When we specify the file path, you cannot really copy and paste from the Windows folders because in the Windows, when they have you copy the file path, it will be like C column now, then followed by the forward slash, right? Uh, so if you do that, it doesn't work. You have to change it. So no, I'm sorry. So in the Windows, it will have the backslash. So like that. Uh, uh, slash is so this is the forward slash. Backslash is this. So C like that. So you have to change this, change the backslash to the forward slash. Or you can use the double backslash. So this one works. This one works. But if you copy and paste directly from the uh, file path, they usually use the backslash, single backslash, which doesn't work. So that's the tricky part. So when you copy and paste, make sure that you either change the backslash to the forward slash, like this, or you add another backslash. So in that way you have double backslash. That also works. Okay, but for the you can also reading the data directly from the web. But that is easy. That is just copy and paste. It works. So if you have a TXT file uh, online, you can just copy the link and then just use that as the locations, and then you can reading the data directly. Okay, and for the read dot tables, there are some options like the SEP, that's the separation. Okay, so how to separate the data point by data point? If you have this one, that's the tab delimited data. Okay, sometimes it's separated not by this, but by comma. So then the SEP should equal to comma. Okay. Okay. Sometimes it's not by comma, it's just by a blank space. So that's the SEP. And also the header equals true or false. So that means the first line, the first row of the data file is the header of the variable name or what? Is the header of the data set or not? If it's true, then they will just reading the first row as the variable's name or the column names. Then the start from the second row, it will be the first observations values. Okay, so there are other options. Just look at the help menu. So you can also reading the CSV data files through the read.csv. Okay, and you can also import the data from other statistical package like the SAS. If you use SAS before, and you can output the data from SAS, and R can reading the data that exported from SAS, and not just SAS for the status, for the S plus, Minitab, Systat, and Python, all these can be read into R. Okay, so the main package in R to read in the data from other statistics package or softwares is called foreign. So keep in mind, if you want to reading a file which is export from another package from or like Python, just look for the foreign package and you can find the corresponding function that allows you to reading the data. Okay. And also you can import the data from the Excel. If you import from the Excel, nowadays people use the XLSX. For this one, there were several package allows you to reading the Excel data. So one of them is the XL Connect. Okay, and there were others like here I'm listing there's a library called XLSX, and there is there's a G data. So there were a few package allows you to reading the uh, data from the Excel spreadsheet. However, the key point is that if you have relatively large data set, like the megabytes, if the file size is megabytes, or let's say you have like almost a million samples, uh, 10, 20, hundreds of variables, a huge data set, don't save it as a Excel and reading to R because that takes a long time. So reading the data to R through the Excel spreadsheet, that takes very long time. So what should we do? The best way is if you have a large data set, try to save the data into the TXT file. That's the fastest, or the CSV file. So the CSV or the TXT file, these are the two fastest data format to reading to the R if you have a large sample size, large data set. Okay, or you can so if it's a small data set, that doesn't matter. You can easily read into the Excel through this package. Okay, so that's the important thing. Okay, and also you can export the data from the R's using the write.table function. You can write out you can export the data as a TXT file or as a CSV file. And also you can export as an Excel file. That's also fun. And if you want to export some large data, like you have a few thousand rows, a few hundred columns. Okay, so if you want to output a large data, that using this can take time. So using this function, which makes it much faster, that's called write.matrix. And that function is in the math library. Okay, so keep in mind. And also we can export the graph from the R's. You can export the graph using different functions. There are many functions in R allows you to output uh, different types of uh, different format. Like the PostScript allows you to output the PS format, and there are PDF functions allows you to output the PDF files as a PDF, and the PNG, JPEG, BMP, and there are many others. So there are many functions in the R that allows you to export the graph into different types of format. And also you can printing directly. Like if you have a R and you want to do some plot like a plot like here, you generated this plot. If you want to use R or use Word, you can just copy and paste. Right click and then copy and then paste into a Word file. So copy and paste, that also works. And also you can save as a meta file or a PostScript file. Or you can highlight that and you can have save as different types of. So it allows you to save in different file format. For the JPEG, it also allows you to change the qualities. So that affects the file size. So that's another way. Okay, so this is to export the graphics from the R. Any questions? Okay, so this is the roadmap of generalization of linear models. So in this course, that that plot shows almost all types of generalization of linear models. Okay, like the linear model is LM, and that's the multivariate linear model. So what is multivariate linear model? That means if we have more than one response variable, or if we have more than one dependent variable. So that we'll call the multivariate linear model. That's MLM. That's the nonlinear models. So if the linear model assumption does not hold, we can fit nonlinear models. So that's this one. Okay. And this is the generalized linear models. Okay. This is the linear mixed effect models. Okay, so what is mixed effect models? So linear mixed effect models means that we have some variable we can consider as a random effect, and some variable we can have a fixed effect. So in that case, so we have two types of effects, not just the fixed effect, but also mixed with the random effects. Okay, so in that way, we can fit some linear mixed effect model. For example, like we can fit the uh, like the spatial effects as a mixed effect, as a random effect. And there are, whether X has a fixed effect, but the spatial, let's say Z, as a spatial variable, that could be random effects. Okay, so these are mixed effects, and this is the generalized additive models, and this is the generalized linear mixed effect models. Okay, so these lines are the showing the generalizations relationships. Okay, so linear model can be generalized in different ways. This is to generalize the linear model in the nonlinear ways. This is to generalize the linear model to the including the random effect variables. And this is to generalize the linear model to not just using the normally distributed dependent variables. We can have different types of distributions like logistic regressions and some other types, Poisson distributions. And this is to generalize the linear model to more than one response variable. And this is to further generalize to not just the linear effects, but also including the nonlinear effects. So that's called additive models, and so on. So in this course, we will cover linear models, we will cover the generalized linear models, and we will cover the generalized additive models. But we have, our department offers some other courses that covers the rest of these models. Okay, so that's the roadmap for the generalization of the linear models. So the prerequisite for this course is you at least should be familiar with the linear regression models, okay? Because that's our starting point. Okay, so explanation of those acronyms. So for the linear models in R, I'm just listing those just a few R functions. that can be used to model these different types of models. But there are many other R functions and many packages available to do the similar jobs. So I'm just listing those most common. So LM and AOV, these are the very useful functions to do the linear model fittings. Okay, for the multivariate linear models, that means we have multiple response variable. Like the most common one is the MANOVA. Okay, so that's the multivariate version of the ANOVA, called the MANOVA. And the generalized linear models, we have a GLM function, and we will talk about the GLM in about 2 or 3 weeks. Okay, and the linear mixed effect model, so that's we have the LME and AOV, so they both can handle the LMM. And the nonlinear models, we have the NLS function there. And nonlinear mixed models, that's the NLME. So that's actually also the extension for the linear mixed models with the nonlinear effect. Okay? And the generalized linear mixed models. So that can be implemented in the GLMMPQL function. And the generalized additive model, which we will talk about later, also the GAN function. Okay? So these are the useful functions in the R that can fit these different types of models. Okay? And for all these functions, most of these, I wouldn't say all of them, but most of these, they use the similar model formula type. So that's why if you understand the meaning of these symbols, you can actually easily write out the model formula for all kinds of functions in the statistical modeling. Okay, so the symbol plus means including that variable in the model. And the symbol minus means exclude that variable in the model. Okay, and the column is X, column Z includes the interaction between X and Y. Okay, and this X star Z, that's the include X and Y interactions. And the vertical column X, Z, that the conditioning, that's the including the X given the Z. Okay, and this one is showing the interaction up to how many ways. Okay, so that means 3, including the main effect, two-way interaction effect, and 2 3-way interaction effect. Okay, and the capital I means that as is, like I X star Z, that means including a new variable. And how to get that new variable? That new variable is actually the product of X and Z. So we include that as a new variable in the model. So these are the symbol meanings in the model formula in R. Okay, so for, that applies to most of the functions. Okay, so let's see some examples. Like a Y, we always in R, we always put the response variable on the left side, then separated the response and the explanatory variable by the tilde. Okay, so Y is the response, tilde X. So that means it's a simple linear regression. Okay, so Y tilde minus 1 plus X. What does minus 1 mean? Minus 1 means through the origin. So minus 1 means without the intercept. Okay, so I want to fit a model. So usually the simple linear regression model looks like what? Y equals to what? Beta 0 plus beta 1 X plus epsilon. Is that right? So that's the usual simple linear regression. Okay, if we have a linear model through the origin or without intercept, that becomes y equals to what? No beta 0, but beta 1 x plus epsilon. In other words, the beta 0 is enforced to be what? To be equals to 0. So if we do that, that means it's this model. Okay? And then y tilde x plus x squared. So that's the quadratic regression. And this is the multiple regression with x1. That's the one of the variable x2, another variable x3 is another variable. So that's the multiple linear regression. And that's y tilde dot. That dot is very useful because that means including all the other variables except y in the data. And that is useful because sometimes if we have let's say 50 variables, we don't need to write out these 50 variables name in the formula. We can just have y tilde dot. That means include all the other variables in the model, okay, except y. If I want to include all the variables except y and x1, then I have y tilde dot minus x1. That means all variable except x1. And this one is the two-way interaction between A and B plus the main effect for A and B. That is the same as this one and the same as this one. So all these three specifications, model formulas are exactly the same, but in different ways. Okay. And the last one is the response is what? Not the y, but the square root of the y as the response over the x plus x squared. Okay, so the last one is the quadratic regression, but the response is square root of y. Okay, so I think that's oh yeah, this is the last one. So that's the generic functions for the statistical inference. Okay, so the the common one is the coif function that to extract the coefficient of the models. So if you fit it a model and save that model into the OBJ, so let's say OBJ is the model object that you fit it in the R. And then you have the coef parenthesis OBJ, that model, it will show you the coefficient. Okay, and like the next one is the resid. It will show the residuals. Fitted, it will show you the fitted values. Summary, it will show you the model summary. And this one is to do the prediction for the new model on some data sets. Okay, and this is the deviance to get the residual sum of squares if it's least square, or the deviance for the linear or generalized linear models. We will talk about the deviance when we reach the generalized linear model. Okay, so these are the common functions for the inference. Okay, any questions? So next Tuesday, so what I will do is I will show you some FOBs, show you some examples like the Boston housing data and the FOBs data, and you can get familiar with those R's through these examples, and also get familiar with those linear regressions, how to fit linear regression models in R's, and how to do some simple inference and fitting the models, predicting the data points through these examples. And also in the Boston housing, I also have how to select the variables in the linear regression model. So that will be the plan for the Tuesday. Let me see, there's a question.
Actually, I would like to ask what's going to be the paper, the material for next week?
I didn't hear clearly. So, what's your question?
Okay, if the material for next week, is it going to be from you?
First, let me stop sharing. So, I think I can. Mm,